Hi guys, welcome to our next session. Today we're gonna do fullerene. We done diamond, we done graphite. These are, as you remember, allotropes of carbon. Today we're gonna do fullerene. So fullerene is actually a laboratory made specimen, meaning it's made in the laboratory. So chemists came together in the laboratory. They took a sheet of graphite. If you remember, graphite was in layers. They took a layer of graphite and they formed it into a ball shape. That ball shape is what we call fullerene. It's a different allotrope of carbon that humans actually made. The particular one we're going to talk about today is 660 fullerene. So the 660, the 60 in the name indicates the number of the carbon atoms forming that specific fullerene sample. There are fullerene samples with more carbon molecules, but we're not going to go in detail. Differently from diamond and graphite, fullerene has a simple molecular structure. As you remember, diamond and graphite, there are giant covalent structures. Because of this, it has a lower melting and boiling point compared to graphite and diamond, and it is not as hard as diamond, and it does not conduct electricity nor heat. Okay. So that was the last part of the covalent bonding. Now we're gonna carry out into metallic bonding. So when we say metallic bonding, it's actually how metals atoms are held together. As you see a sheet of metal somewhere or a bar of iron, it's a solid, the atoms are held together, but why are they held together? How they are attracted to each other, basically. You probably know metals, they have really high melting and boiling points. They are really strong materials. So basically, we're going to look at the molecular structure and explain why do they have these properties. So, give an example, sodium is a metal. When sodium atoms bond together to form a solid sample of sodium metal, the outer electrons on each sodium atom, so as you remember, sodium is in group 1. Hence, it has one electron in its outer shell. Only one. So this electron, it becomes free to move throughout the whole structure. The electrons now are said to be delocalized. Okay, this word is important. These electrons are no longer attached to particular atoms or pairs of atoms. Instead, you can think of them as flowing around through the whole metal sample. When a sodium atom loses its outer electron in this structure, sodium ion is Na+. As it loses one electron, it will have the same number of protons. So what happens? It gains a plus charge because it has more protons than electrons. And as you remember, protons are positively charged, electrons are negatively charged. But because they are in same numbers in normal atoms, they neutralize the charge of the atom. When you talk about an ion, if you lose one electron, then you have more protons, which means you have more positive charge. If you lose one electron, you have one positive charge. Again, a sodium ion is formed. A metallic structure consists of a regular arrangement with what we call lattice of positive ions in a sea of delocalized electrons. And the next line is the definition of metallic bonding. Metallic bonding is the electrostatic forces of attraction between each positive ion and the delocalized electrons. Okay, that's really important. And carrying on, so metallic bonding, second part, metals form a giant structure through metallic bonding. The ions, as you know, the cations, because they form positive ions, formed by metals. Metal depends on the number of electrons the original atom has in its outer shell. So it depends on the group. If you're in group 2, then you will have 2 delocalized electrons per each atom, and you will have a positive 2 charge. So if you look at the diagram, and you have to draw this diagram to your notebooks as well, you don't have to draw all of these. You can just draw a couple sodium atoms, sodium ions, sorry. But it is important to show they are regularly arranged. Okay? So you have the metallic structure of sodium atom, you have the lattice of sodium ions, and you have sea of delocalized electrons. So they actually flow through these, and the electrostatic attraction between these positive ions and these negative flowing electrons hold the structure together. So you can think of these electrons as glue in between grains of sand. So to do a checklist, so pay attention to the lecture and my sentences, write down the notes on the slides to your notebooks, have a look at the videos I recommend to you, do your homework and revise. This time we're gonna watch the video together. Let's carry on to the video. Yes. Let's start.
Metals are used.
By the way, you can pause the video and carry on the video after you wrote down your notes. It doesn't matter, it depends on you.
Metals are used in many everyday objects. This morning, when I woke up, I decided to have a soft-boiled egg and a cup of coffee. The pot I used is made of metal. The kettle is made of plastic, but the coiled heating element inside it is made of metal. Metals are good conductors of heat. This is the reason why metals are used to make these everyday objects. You would never see a pot made of wood or a heating element made of plastic. Metals are also good conductors of electricity. The wire connecting your kettle to the electrical socket.
So a lot of this video is about what we're going to do next. We're going to talk about the properties of metals. But we first discovered what is the structure. So you have delocalized electrons. Does this tell you? What this tells you is that these delocalized electrons are free to move. Okay, if they're free to move, they will be able to carry electricity and heat. So they will be good conductors. Okay, that's why metals are good conductors. Carrying on.
Is actually made of many copper wires, insulated with a layer of rubber. Think about the shapes of the everyday objects we described. The pot, the heating element inside the kettle, and the copper wires. Notice that they are very different. Metals are malleable. This means that they can be molded into different shapes. Metals are very ductile. This means that they can be stretched into wires. To fully understand these properties of metals, we must understand metallic bonding. When we talk about metallic bonding, we are actually describing the electrostatic attraction between the metal ions arranged in a lattice structure and the free-floating electrons around them.
So a lattice is a regular arrangement of atoms. If you can write this down, it'll be great. Write this down as a note.
These electrons are free to move around. The term sea of electrons is also used. What is a lattice structure, and where have you heard this term before? Let's pause the lesson to think about this and resume when you are done.
So we didn't actually do this in detail, but lattice is a regular arrangement. Okay, that's all you need to know about it. It's a regular arrangement of something. In this case, it's a regular arrangement of sodium ions in metallic bonding. Okay?
The term lattice structure means that there is a regular repeating pattern. We have heard this term before when discussing ionic lattices. It is used to describe the alternating positions of the metal and nonmetal ions. In metallic structures,
Don't worry about that part.
however, there are only metal ions. These metal ions are arranged side by side in a regular repeating pattern. The free-floating electrons act like a glue and hold the structure in place. This is a very strong attraction and explains why metals have high melting and boiling points. A lot of heat energy is needed to overcome this attraction. This is also why metals are very good conductors of heat.
See again, this strong attraction. You can think of these electrons as glue, holding them together. Because the attraction is really strong, you have really high melting and boiling points. So it's really hard to melt metals, as you know.
Free-floating electrons are the reason why metals can conduct electricity. Metals are malleable and ductile because no matter what shape the metal takes, the free-floating electrons will conform to that shape. The strong electrostatic attraction will remain, and therefore the structure stays intact. Let's think about it. Cars and bicycles, trains, planes, buildings, cutlery, spectacles, furniture, and endless items can be made from metals. To recap, the electrostatic attraction between metal ions arranged in a lattice structure and free-floating electrons is known as metallic bonding. This explains many properties of metals. They are good conductors of heat and electricity, have high melting and boiling points, and are malleable and ductile.
Yes, guys, that's it for today. This time we done the first part of metallic bonding. Now we're gonna do the second, and this will be our actually our last topic in this turn. Okay, remember the checklist, and yeah, talk to you again. Thank you.